Jimmy Akin's Mysterious World is brought to you by the Star Quest Production Network and is made possible by our many generous patrons. If you'd like to support the podcast, please visit sqpn.com/give. You're listening to episode 206 of Jimmy Akin's Mysterious World, where we look at mysteries from the twin perspectives of faith and reason. In this episode, we're talking about how we found the universe. I'm Dom Bettinelli, and joining me today is Jimmy Akin. Hey, Jimmy.
Howdy, Dom.
Folks, throughout human history, people have wondered about the world around us. How did it begin? How was it structured? Are we living on a flat Earth? Are we living on a ball? Are we at the center of the universe? What are the planets? How far away are the stars? Well, we'll be talking about all these questions and more on this episode of Jimmy Akin's Mysterious World. So, Jimmy, why is today's episode titled How We Found the Universe? And why did you want to do this mystery?
The title refers to how we found the structure of the universe, the way it's put together. And I wanted to do the mystery because it's a really cool story. The nature of the universe has been a mystery for virtually all of human existence, and it's only been recently that we've gotten answers. And there are still mysteries left to find out. So this will be a foundational episode that will set us up for other mysteries in the future.
So then how will we be proceeding today?
We're going to start with the oldest view of the world, so far as we can tell, since it's a prehistoric one. It did survive into historic times when writing became available. And after we look at that, we're going to show you step by step, one building block at a time, how that worldview changed until we arrived at the present understanding of the universe. It's a fascinating story, and it represents a triumph of the intellect and abilities that God gave us. I love the twists and turns in this story and how key figures brought us to the next stage in it.
Will we be talking about the age of the universe and the Big Bang?
Not today. There's a whole other set of stories for that mystery, so we'll cover that in the future episodes. This time, we'll be looking at the physical structure of the world and how people figured it out.
Great, then let's begin. How did the ancients envision the structure of the world? They didn't imagine the vast cosmos of distant galaxies that we do today.
No, and although the earliest cultures didn't leave written records, we still have a pretty good idea of how they usually conceptualize the world. Since human beings live on the surface of the Earth, and the Earth is so big that from the surface it looks flat, prehistoric humans tended to believe that the Earth is flat. That seems obvious from an ordinary perspective on the Earth's surface. Also, since the sky seems to curve over the Earth, the sky was often conceived of as a kind of inverted bowl that was set over the Earth. And since the major celestial objects, the sun, the moon, and the stars, move around in the sky in circles, they look like they're orbiting the Earth. So ancient peoples would tend to think that the Earth is at the center of the cosmos with everything moving around it. Flat Earth, domed sky geocentrism is thus probably the original view of the cosmos for ancient peoples all over the world. Those three things, the flatness of the Earth, the dome shape of the sky, and the location of the Earth at the center of everything, were probably shared virtually everywhere.
So when did that start to change?
So far as we can tell, in the first millennium BC, within a few hundred years of each other, several cultures began to realize that the Earth isn't flat, but is actually a sphere. This happened in Greece, India, and China, for example. And there were various arguments that they used to show that the Earth is a sphere. For example, Aristotle offered several arguments to demonstrate the spherical nature of the Earth, and we discussed those back in episode 68 on the flat Earth theory, so listeners can review that for more information. Greeks also started doing calculations to do things like estimate the size of the Earth and the distance to the Sun. Around 240 BC, the astronomer Eratosthenes used the shadow of the Sun on the summer solstice to calculate the circumference of the Earth as 250,000 stadia, which is only around 11% off from the modern estimate of 24,860 miles. So the first element of the primitive worldview, the idea that the Earth is flat, was now replaced by the belief that it's a globe.
What about the other two elements of the primitive worldview, that the sky is a dome and that the Earth is at the center?
If the Earth is a sphere rather than a flat surface, it would be weird to think of the sky as a dome set on top of it. But since the sky does seem to bend around the Earth, the sky began to be conceived as a sphere also. The idea that the Earth is at the center, though, still remained dominant, though it was actually challenged by some. The Greek Pythagorean school of thought proposed a really interesting view of the world in which the Earth is not at the center and neither is the sun. Instead, according to this theory, which is attributed to the Pythagorean philosopher Philolaus, who lived around 400 BC, everything actually orbits an unseen body referred to as the central fire. The Earth goes around the central fire once a day, and the sun goes around the central fire once a year.
If the Earth goes around it once a day, why don't we see the central fire?
Because one side of the Earth is always turned toward the central fire, and we don't live on that side of the planet. Now, they didn't have the concept of tidal locking in the ancient Greek world, where two bodies influence each other gravitationally, so at least one of them gets locked so that one face is always towards it, like our moon is tidally locked to the Earth, so we always see the same side of the moon. But basically, the Pythagorean view was that the Earth is tidally locked with the central fire. So one side always faces it, and you only get to see it if you live on that side. Another cool feature of this system is the Pythagoreans believed that there was another hidden planet, which they called Antichthon. The word Antichthon means CounterEarth in Greek, and they apparently thought that the CounterEarth orbited opposite our planet on the far side of the central fire, so we never got to see it.
Yeah, the idea of a counter-Earth has appeared in science fiction stories, but given what we know now, is this kind of world scientifically possible?
It's more possible than you might think. There are 5 gravitationally stable points generated by the orbit of the Earth around the Sun. These are known as Lagrange points, and because they're points of equilibrium, they can have masses at them. For example, asteroids and dust can come into Lagrange points and get stuck there. And the third Lagrange point, known as L3, is directly on the opposite side of the Sun from the Earth. So in terms of the celestial mechanics, there could be a body there, even a big one like a planet. Unfortunately, as cool as a counter-Earth would be, it seems that we don't have one in our solar system. If there were one, we would have been able to detect it in various ways, such as by its gravitational influence on our space probes, which would go off course if there were a hidden planet in the inner solar system. So there might be some dust and asteroids at the L3 point, but nothing as big as a planet.
Most of the ancient Greeks weren't Pythagoreans, so they wouldn't have believed in the counter-Earth or the central fire. Were there others who rejected the idea that the Earth is the center of everything?
There were. In the 200s BC, Aristarchus of Samos proposed that the Earth isn't the center of the universe. He thought the sun was at the center of everything, and he had some followers, though most people still adhered to the idea that the Earth is at the center.
And what model of the universe became the common one?
It was a variation on Aristotle's model, which he developed around 350 BC. Aristotle based his version on earlier models, but he then put his own spin on things. Now, since Isaac Newton wouldn't live for another 2,000 years, Aristotle didn't have the idea of gravity. But he did have something similar to it. He believed that every object in the universe would seek its natural place, and where an object's natural place was would depend on how heavy it was. So Earth, being the heaviest of the 4 classical elements, would have its natural place at the lowest point. All of the Earth in the universe would thus clump down in the center point of the universe and make a sphere, which is one of his arguments for why the planet Earth should be a sphere. Water, the next heaviest of the 4 classical elements, would then clump around the Earth, which is why the planet Earth is covered with seas and oceans. Air, being lighter than earth and water, would then find its natural place above the waters, which is why we have an atmosphere. And fire, being the lightest of the classical 4, as you can see from the fact that it tries to leap upward in the air, would have its natural place up really high.
Does that mean Aristotle thought that there was fire in outer space?
Actually, no, because he thought there's a fifth element called ether. Ether is so light, according to Aristotle, that we don't have any of it down here on Earth. Its natural place is too high up for us to get to, and it's what everything in space is made out of. Ether is also incorruptible and unchanging, which is why you don't see the sun, the moon, and the stars ever change. You know, they just go about their business endlessly circling round and round. So everything down here on Earth is made of the classical four elements, but everything in space is made of the fifth element, ether. The dividing line is the sphere of the moon. The moon and everything above it is made of ether, but everything below the moon is made of fire, air, water, and earth.
You just mentioned the sphere of the moon. We think of the moon itself as a sphere because it's round, but that's not what you mean, is it?
No, one of the things that Aristotle had to account for was the motion of the sun, the moon, and the stars. And since he didn't have the idea of gravity, he couldn't say that it's their gravitational interactions that pull them around in the sky. Aristotle also had a couple of beliefs that sound reasonable, even though modern physics has rejected them. One of his ideas is that there's no such thing as a vacuum, that you can't have space that's totally empty. And he had a really interesting argument for this. I'll put it a little differently than he did, but think about what would happen if someone buried you up to your neck in earth. You would find it really hard to move. But if you were standing in water up to your neck, like in a swimming pool, it would be much easier to move. You'd still be slower than you are normally, but you could still wade through the water. Now, if someone then drains the water out of the pool so that you're moving through air, you can go quite quickly, walking or even running if you want. The principle that we see is the denser the matter you are trying to move through, the slower you go. So what would happen if there was no matter at all? If you were in a total vacuum with zero density, you'd be able to move faster yet. And according to Aristotle, you'd be able to move infinitely fast. But infinite speed causes problems. That's why it's actually a good thing that the things in our universe are normally limited by the speed of light, because if they weren't, if things moved infinitely fast, it would basically break the universe and causality would be completely messed up. We'll have a link to a video you can watch about what would happen if the speed of light was infinite. Now, Aristotle didn't know about the speed of light, but it's clear that if you look up at the sky, the sun, moon, and stars are not moving infinitely fast. So for Aristotle, there must not be a vacuum up there. There's always some density of ether, keeping things from moving infinitely fast in the heavens.
You said there was another belief Aristotle had that seems reasonable, but that modern science has rejected. What was that?
He believed that there is no such thing as action at a distance. If one object is going to have an effect on another, then there has to be some kind of physical connection between them. Like if you're going to hear my voice, we need air as a medium between my mouth and your ear. If we had one of those fanciful infinite speed vacuums between us and no air, then you wouldn't be able to hear me no matter how loud I tried to make my voice, because it wouldn't carry across the vacuum. So Aristotle's rejection of action at a distance and his rejection of the idea of a vacuum went hand in hand, since they allowed him to give an explanation for how the sun, moon, and stars move. Basically, he thought they were embedded in transparent spheres. For example, the lowest transparent sphere had the moon attached to it, and as that lowest sphere turned, the moon moves across the sky. Aristotle, like many others, thus thought that the universe was a series of transparent spheres nested one inside another, like one of those Russian Matryoshka dolls, where you open the doll and there's another doll inside. Earth is at the center of all the transparent spheres, the moon is on the lowest sphere, and the sun and the planets are on spheres further up. And then the fixed stars, the ones that don't seem to change their positions, the constellations, are on the outermost sphere. Now, the easiest motions to explain were those of the sun, the moon, and the fixed stars, because they just go around in circles. But planets can wander about the sky, which is why they're called planets. Planetes is the Greek word for wanderer. Planets can even seem to move backwards in the sky when the Earth catches up to them and then passes them in its own orbit. Like when you're driving down a highway and you pass another car going in the same direction as you. If you look out your window as you drive past, it looks like the other car has started moving backwards. And as the Earth passes other planets in their orbits, they seem to move backwards too. But if you don't think of Earth as moving, if you think it's motionless at the center of a bunch of transparent spheres, then you need to account for how the planets start moving backwards in the sky another way. Basically, you need a really complicated set of spheres, and based on the calculations of earlier scholars, Aristotle thought that there were something like 47 or 55 nested spheres in the universe.
Now, when people think about early cosmological systems today, they don't normally think about Aristotle's system. Instead, they think of what's called the Ptolemaic model. Why is that?
Because it's an improvement on Aristotle's system. Aristotle articulated a good overall system that explained things, but he didn't provide lots of detailed calculations to predict the motions of the individual planets. He deferred to other scholars on that. And over time, the other scholars got better at predicting these motions. So the core of Aristotle's theory was accepted, but the details got changed. And the guy who came up with the most successful tweaking of the Aristotelian system was named Claudius Ptolemy. So his version is known as the Ptolemaic model. Ptolemy was a Greek who lived in or around Alexandria, Egypt in the 2nd century, so he was alive in Christian times, and there was already a community of Christians in Alexandria in his day. In fact, the Alexandrian church reportedly was founded by St. Mark, St. Peter's companion and the author of the Gospel of Mark. We won't go into the details of the tweaks that Ptolemy made to Aristotle because they're rather technical and kind of hard to explain without diagrams for our audio listeners, but basically he produced an upgrade that better predicted the exact motions of the planets, and his model became standard for over 1,000 years.
But when did that start to change?
In 1543, when the Polish scholar Nicholas Copernicus published a book called On the Revolutions of the Celestial Spheres. This brought about what is known as the Copernican Revolution, and it was one of the early events in the scientific revolution. One of the reasons Copernicus undertook this work was he wanted to help with the reform of the calendar. At the time, people were using the Julian calendar, which goes all the way back to Julius Caesar. But the Julian calendar's estimate of the length of the year is slightly off. And so over the previous 15 centuries, the calendar had started to get out of sync with the seasons. And so there was interest in revising the calendar to fix the problem. Just 40 years after Copernicus's death, Pope Gregory XIII did revise the calendar, giving us the Gregorian calendar that we use today. And Copernicus contributed towards that effort. He wanted to contribute to the goal of fixing the calendar by coming up with a better way to do astronomical calculations. So he reached all the way back to Aristarchus of Samos and his sun-centered model of the universe with the planets moving around it. And Copernicus knew about Aristarchus's theory. He even mentions it in a draft of his book. Copernicus thus proposed something similar to Aristarchus, except instead of saying that the sun is at the exact center of the universe, Copernicus proposed that it was near the center of the universe.
How radical was Copernicus's theory at the time?
Not as radical as you might think. For a start, he didn't get rid of the celestial spheres. They're even referred to in the title of his book, On the Revolution of the Celestial Spheres. At this point in history, we're still a century away from Isaac Newton and the theory of gravity, so Copernicus was still working with Aristotelian physics. As a result, he still had the transparent spheres made out of ether. He just arranged them differently. He took the sun off a transparent sphere and made it motionless near the center of the universe, and he put the Earth on a transparent sphere and had it moving around the sun, as well as rotating on its axis. The spheres of the other planets he just reordered so that they were centered on the sun instead of the Earth, except for the moon, which he did have on a sphere orbiting the Earth. And he still had the outer sphere of the fixed stars, which he held were very far away and motionless. The apparent motion of the fixed stars was caused by the Earth turning on its axis in his model.
Was Copernicus's system an improvement on Ptolemy's model?
In some ways, Copernicus thought it was an improvement in that it was more elegant, but in other ways, it was even more complicated than Ptolemy's. You see, everybody, including Copernicus, was assuming that the stars and planets must be moving in perfect circles, and they don't. But the circle was considered a perfect shape, and the celestial bodies seemed to move in almost perfect circles, so people assumed that perfectly circular motion was what they did.
Then how did they explain the actual motion of the planets in the sky?
One of the ways was by adding circles upon circles. In Greek, the word for circle is kuklos, and the word for on is epi. So a circle on a circle was called an epikuklos, or an epicycle, as we say in English. Epicycles have been used to explain the observed motions of the planets since the ancient Greeks, and they featured prominently in Ptolemy's model. But when Copernicus reordered everything and made the planets go around the sun, he scrapped some elements of the Ptolemaic system, and to compensate for those, he actually had to add more epicycles than Ptolemy used.
Was that what caused astronomers not to immediately accept his model of the universe?
No, a bigger problem was making the Earth move as a planet. I mean, people had had nearly 2,000 years to get used to the idea of ether, that the stars and the planets were made of this super lightweight substance that moves in circles by its own nature. But Earth is manifestly not made of ether. The Earth is made of Earth, and Earth does not move by its own nature. In fact, it can be really hard to move Earth, which is why faith strong enough to move mountains is considered really strong faith. So if you've got this huge, enormous sphere made out of Earth, what would make it move? Why would this super heavy planet we're on be zipping around the sun just as fast as the other lightweight ethereal planets? Without a theory of gravity, this seems extremely counterintuitive. So, no, people did not immediately rush to embrace Copernicus's model.
And they didn't after Galileo either.
No, and by the way, we will be discussing Galileo in future episodes. But in this period, the standard model of the universe was still one that had the Earth at the center and a bunch of concentric transparent shells, with the planets moving in perfectly circular paths, although sometimes they were complicated by the use of epicycles, or circles on circles, and then with the shell of the fixed stars as the final sphere outside the orbit of Saturn, which was the farthest planet that can be seen with the naked eye. But things did start to change over time, and those elements, the planetary shells and the epicycles and the shell of the fixed stars, began to fall away.
And when did the first one fall?
Well, I don't have polling data from 16th century astronomers to track its decline, but the key moment that led to its fall occurred in 1577. At this time, one of the most prominent astronomers was a Danish man named Tycho Brahe. He has an interesting life story, which includes the fact he had a metal nose.
Okay, so time out. We have to hear that story. Why did Tycho Brahe have a metal nose?
Because he lost his biological nose in a duel with a nobleman who happened to be his third cousin. In early December of 1566, when Tycho was 20 years old, he and his third cousin were both attending an engagement party being hosted by a local professor. And after indulging in the refreshments a little too much, Tycho and his cousin were drunk, and they got into an argument about who was the better mathematician, as you do. This was, in fact, not uncommon in this historical period, and it was not the only time that people took their mathematical competitions way seriously. Also, at this time, noblemen would duel each other over all kinds of personal slights. They would duel at the drop of a hat, especially if the hat was yours and the other guy knocked it off your head and slighted you. So, with Tycho and his cousin both feeling slighted, they decided to do the only thing they could do and settle who was the better mathematician by attacking each other with swords. Now, duels like this typically weren't to the death. Whoever drew blood first would consider his honor satisfied, and that's really all they were after in this case. The duel didn't take place on the night of the engagement party, but later in the month, so they were sober. However, it did take place at night, so the duelists couldn't see each other very well. And instead of just giving Tycho a token injury, his cousin accidentally slashed off his nose. As a result, Tycho wore a metal nose for the rest of his life. He reportedly had a gold or silver one, which he may have worn for special occasions, but recently his remains were exhumed and they could tell by the metallic residue that the nose he wore most of the time was actually brass. In any event, by having a replacement metal nose, Tycho Brahe may have been the world's first cyborg astronomer, which is wicked awesome. Cyborg astronomers are cool. And good news, he and his cousin patched things up after the duel, and his cousin actually became one of Tycho's biggest supporters.
You could say he lost that duel by a nose.
Oh, yes, you could.
Okay, so now that we know how he got his metal nose, what happened in 1577 that changed one of the key things people thought about the universe?
In that year, Tycho and his metal nose were looking up at the sky, and he saw a comet. Now, comets were nothing new. I mean, people had been seeing them all through history, but they didn't realize they were in outer space. I mean, remember, people thought that from the moon upward, the heavens are perfect and unchangeable. The stars and planets just move around the way they always do, but they neither come into existence nor pass out of existence. So what do you make of it when a comet shows up? On the one hand, they are a light in the sky, so they're like a star, but they also have these long tails. And so in Greek, a comet came to be known as an aster kometes. Aster for star, and kometes means long-haired. So a comet is a long-haired star. And maybe that made it different enough from the other stars that it wasn't in outer space. After all, unlike the unchanging fixed stars, comets most definitely appeared and then disappeared, so they didn't seem changeless like the things in the heavens were supposed to be. Thus, Aristotle concluded that they weren't in space. In his book, The History of Astronomy, a very short introduction, Michael Hoskin writes,
For Aristotelians, the comets coming to be and passing away amply demonstrated their terrestrial, or more exactly atmospheric, nature. As Aristotle himself had explained, comets resulted from the effect of the rotating heavens on the air and fire that surrounded the Earth. So whenever the circular motion stirs this stuff up in any way, it bursts into flame at the point where it is most inflammable. As long as the heavens had been changeless, there had been little reason to dissent from Aristotle's claim that comets were atmospheric.
So comets could be explained as atmospheric phenomena produced in the upper atmosphere where Aristotle's spheres of fire and air intersect. And there wasn't reason to challenge that as long as the rest of the sky seemed changeless. But that changelessness changed in 1572 when a supernova occurred. This supernova was bright enough you could see it in the daytime. And I'll confess, one of my life goals is I would like to live long enough to see a daytime supernova. I think that would be awesome, as long as it's not close enough to harm us on Earth. In any event, Tycho was one of the people who saw the supernova. And in fact, today it's called Tycho's supernova, and we'll have a link so you can read about it. It got Tycho wondering about the immutability of the heavens, because they don't seem very changeless if new stars can appear, especially new big bright ones you can even see in the daytime. That made him wonder about comets and whether they're really in the atmosphere or not. And Tycho was in an excellent position to settle that question because he really was a good mathematician. though having a duel with swords may not be the best way to prove that. What's more, he was also the best observer of stellar phenomena in his day. He had better measurements of where things were in the sky than anybody else. So by taking different readings and triangulating, Tycho could figure out how high up a comet really was. Hoskin states,
if only nature would provide him with a bright comet, he would measure its height and establish whether it was atmospheric or celestial. In 1577, when Tycho's observatory, the Uraniborg, was under construction, nature obliged, and Tycho established that the comet was moving freely among the planets.
Tycho realized this had profound implications for the structure of the universe. If the comet was traveling among the planets, it would crash into the transparent spheres that the planets were moving on, if there were any spheres. Tycho realized the fact the comet didn't crash into these spheres meant that the spheres weren't there. Of course, it took a while for this idea to spread, but Tycho's comet effectively knocked the transparent spheres out of the universe. At least the ones the planets were supposed to be attached to. There was still the outer sphere to which the fixed stars were attached.
So now the universe looks like a big bubble with the fixed stars attached to the outer sphere, with the Earth at the center, and with the planets moving in perfect circles, even if these were sometimes circles on circles. So what changed next?
It was the circles on circles, or epicycles, that dropped out. In the early 1600s, Galileo's contemporary and Tycho Brahe's former assistant, Johannes Kepler, realized that the motions of the planets can be much better explained as moving on simple ellipses rather than having to base everything on circles. And that allowed astronomers to do away with all the complicated epicycles. This idea also took a while to spread, but the mathematics of ellipses had been understood since Greek times, and the new ellipse-based orbits that Kepler introduced resulted in a simple, more accurate set of predictions of planetary motions.
You mentioned that Kepler was a contemporary of Galileo. Well, Galileo is most famous for his defense of a sun-centered universe, but he made many other contributions to astronomy, right?
Yes, and the biggest was popularizing the newfangled invention known as the telescope. Galileo didn't himself invent the telescope, but he did popularize it and apply it to astronomical questions. And as the first person using a telescope for astronomy, he was the first person to get to see a lot of things, and he made a lot of discoveries. Hoskin explains,
until the invention of the telescope, each generation of astronomers had looked at much the same sky as their predecessors. If they knew more, it was chiefly because they had more books to read, more records to mine, but all this now changed. In the coming months and years, Galileo saw with his telescope wonders vouchsafed to no one before him. Stars that had remained hidden from sight since the creation. 4 moons that orbited the planet Jupiter. Strange appendages to Saturn that would be recognized as rings only half a century later. Moon-like phases of Venus. Mountains on the moon not very different from those on Earth. Even spots on the supposedly perfect sun.
Galileo was also able to confirm an idea that had been a puzzle all the way through human history. What is the Milky Way made of?
Let's talk about that. Today we think of the Milky Way as the galaxy we live in, but if the ancients thought of the universe as a set of concentric spheres, there's no way they would have understood it that way. So what did they make of it?
They weren't sure what to think, and they certainly didn't have the modern concept of a galaxy. They started with what was obvious, which is that if you go out in the night and look at the darkened sky without all the light pollution we have today, you'll see a faint band of light that stretches around the circle of the sky. This band of light is faint, and it's not obvious what it is. It's kind of cloudy, and it's whitish in color, so the Greeks called this cloudy whitish circle the Galacticos Kuklos, which means the milky circle, since milk is white. In Latin, they thought of this band around the sky as a road, and so they called it the Via Lactea, or Milky Road. And since way is another word for road in English, although a lot of people don't realize that, but a way is a road. So get out of the way means get out of the road based on its word origins. In English, we call the Via Lactea or Milky Road the Milky Way. But nobody knew what it was. Some ancient philosophers suggested it might be made out of stars, but this isn't obvious because it doesn't look like stars. It looks like a diffused glow. But when Galileo turned his telescope on it, he discovered that the philosophers who said it was stars were right. It's just that the stars in the Milky Way appear too small to be able to make them out individually with the naked eye, so they blend into a diffuse glow. Now, it was known that the Milky Way is made of stars, but people still didn't have the concept of a galaxy. There was just this band of really small-looking stars up in the sky. They might be attached to the same outer shell that the other fixed stars were attached to.
If the planetary spheres were gone, why did people still think the fixed stars were attached to a shell? Wouldn't the fact that some are brighter than others suggest that some are closer and others are farther away?
It might, but there was a problem, which is that nobody could see parallax shifts with the fixed stars. A parallax shift is the way an object's location appears to shift depending on where you're viewing it from. The easiest way to demonstrate this is with a practical experiment. So if you're listening in a place where this is convenient, hold out your hand and stick up your thumb. Then close one of your eyes, look at your thumb with the open eye, and notice what's in the background behind it. Once you've noticed what's in the background, close that eye and open the other one. You'll see that what's in the background has shifted, and that's a parallax shift. This works because your thumb is an object that is close up to you, but it wouldn't work if you were looking at an object that's very far away. For example, if you look at a tree that's half a mile away from you, you probably won't see any shift in the background just by opening one eye and closing the other. And that was the problem with the fixed stars. They're too far away to see parallax shifts with the naked eye. We actually can see parallax shifts with the planets as the Earth moves in its orbit. If you wait 6 months, the Earth will be on the other side of the sun, around 180 million miles from where you took your first observation of a planet, and you can then triangulate using the parallax shift to figure out how far away the planet is. But the stars are so far away that we can't observe parallax shifts with the naked eye or with the early telescopes, which were far too small and weak to detect them. As a result, it looked like the fixed stars were all the same distance away, as if they were attached to a big sphere, and some were just brighter than others. You could propose that the bright ones might be closer, but if they were closer, why didn't we see parallaxes?
How far away did people think the stars were?
Over time, there were different estimates about this. In the 3rd century BC, there was a mathematician and inventor named Archimedes. He's famous for figuring out things you can do with a lever, so Archimedes is the lever guy. He also apparently invented a heat ray that you could use to set enemy ships on fire, so we'll definitely be talking about him in the future. He also wrote a book called The Sand Reckoner, in which he tried to estimate how many grains of sand you'd need to fill up the entire universe. This meant that he needed to calculate the size of the universe, and he estimated it was about 2 light years across. He didn't have the concept of a light year, of course, but that's what he came up with in modern measurements. And this would mean that the fixed stars would be about a light year away from us. And, one side of the shell of the fixed stars is a light year away. The other side of the shell is another light year away with us at the center. And so the universe would be about 2 light years across. In the end, he reckoned that you would need 1 vigintillion grains of sand to fill up the universe. That's a 1 followed by 63 zeros.
Now, did everyone agree with his estimate of the distance to the fixed stars?
No, other people made different estimates, and most were much smaller than Archimedes. A lot of people, using Ptolemy's model of the universe, thought that they weren't much farther away than Saturn. Now, the distance from the Earth to the Sun is called an astronomical unit. So Earth is 1 astronomical unit away from the Sun. And depending on where Earth and Saturn are in their orbits, Saturn can be as close to us as 8 astronomical units or as far away as 11 astronomical units. So the fixed stars might be something like 12 or 13 astronomical units away in a Ptolemaic universe. That distance would put them between the orbits of Saturn and Uranus. And of course, they didn't know about Uranus, but this is where they would be on this model, given what we know now. The fixed stars were thought to be, a little bit farther out than Saturn, but not as far out as Uranus. And that's way, way less than a light year. Saturn is only between 60 and 90 light minutes away. So at the speed of light, you could reach the fixed stars in less than 2 hours. But our metal-nosed friend Tycho Brahe did his own calculations and estimated that the stars had to be farther away than that. Like we mentioned, he was better at precisely measuring things in the sky than anybody else in his day, and he also couldn't find parallaxes. And if he couldn't find parallaxes using his system, well, he knew how precise his system was, so he calculated that the stars would have to be at least 700 times further away than Saturn, or at least 7,000 astronomical units. That would make them 40 light days away, but still nowhere near the light year that Archimedes reckoned.
Who was it that eventually convinced people that the fixed stars aren't on a sphere?
That was the French philosopher Rene Descartes. He's the I think, therefore I am guy. And in the mid-1600s, just after Galileo's death, he published his own theory of the universe, which became very popular. Now, he didn't generally pay much attention to anything Aristotle said, but he did agree with Aristotle that a vacuum or empty space cannot exist. As a result, he thought the universe is filled with matter, and that matter is obviously moving, as the planets indicate. But if the universe is completely filled up with matter, the only way for one piece of matter to move is if the piece of matter in front of it also moves. And so Descartes conceived of our solar system as a big swirling vortex made out of matter with the sun at the center. He also thought of the Earth as being at the center of its own vortex as it went around the sun, and the moon was trapped on the edge of the Earth's vortex, like something going around the edge of a whirlpool. And Descartes thought of the stars as distant suns at the center of their own vortices. So from Descartes, the idea of the stars as distant suns took off. He's the one who popularized that idea. There had been speculation about this idea in antiquity, but it was his vortex-based cosmology that popularized it. An article on the Library of Congress's webpage explained,
in Descartes' system, like Aristotle's, the universe was full of matter. There was no such thing as empty space. To explain motion, Descartes introduced the concept of vortices. The system consisted of different kinds of matter or elements rubbing up against each other. His model included 3 different kinds of elements: luminous, transparent, and opaque. Luminous was the smallest and was what the stars were made of. Earth and the planets were made up of the denser opaque. The space between the planets and the stars was made up of transparent. He stated that luminous matter would settle at the center of these vortices, and the transparent and opaque elements would keep shifting around each other. This shifting created the movement of objects in the heavens. Descartes' theory of vortices solved a series of existing problems for astronomers and philosophers. It was becoming increasingly difficult to keep the Aristotelian notions of solid, transparent spheres intact. Descartes' vortices offered a new mechanism for explaining the movement of the heavens and filled a need to establish an underlying theory to support the new astronomy. As a result, Descartes' ideas about vortices were widely adopted as a way of thinking about the cosmos.
So Descartes' system was popular because it solved problems like what causes the planets to move if they aren't attached to spheres. It's the matter that fills space that pushes them along, like the particles of water in a whirlpool push along things that are floating in the whirlpool. And the smallest pieces of matter, which glow, which are luminous, get sucked to the center of whirlpools and form stars. And even though he's wrong about these different kinds of matter, actually, you do have swirling vortices that form stars and planets that go around each other.
So did Descartes calculate how far away the stars were?
Not that I've found, but he did address the matter. In his book, The Principles of Philosophy, he writes,
"As for the fixed stars, there's decisive empirical evidence that they aren't closer to the Earth or the Sun than Saturn is. But there's no such evidence that they aren't a truly enormous distance from us. Things I'll say later about the movements of the heavens will imply that the fixed stars are so far from the Earth that by comparison Saturn is a near neighbor."
Later on, he says,
You may want to object, given that the Sun always keeps the same position in relation to the fixed stars, the Earth's great year-long circle around the Sun must bring it nearer to any given fixed star at some times than it is at others. But this isn't confirmed by any observations that have been made.
Here, he's referring to why astronomers weren't seeing stellar parallaxes.
The answer is that the fixed stars are too far away from the Earth for these changes of distance to be observable by any means that we have. The distance that I suppose there to be between the Earth and any fixed star is so immense that the whole circle of the Earth's path around the Sun should be counted as a mere point in comparison to it. Some people may find this incredible. I mean, those whose minds aren't accustomed to contemplating God's mighty works, and who see the Earth as the most important part of the universe because it's where men live and they think everything was created for men. But astronomers won't find it so strange, because they already know that the Earth is like a mere point in comparison with the heavens.
So Descartes wasn't specific, but he thought the stars were immensely far away, and his view that the stars are very distant suns became standard. This got rid of the outer shell of the fixed stars and left us floating in a vast sea of stars.
Who was the first person to be able to realistically calculate how far away the stars were?
That was the British philosopher, mathematician, and eccentric Isaac Newton, who lived in the late 1600s and early 1700s. He picked up the idea that he ended up using from a Scottish mathematician named James Gregory, and it let him estimate the distance to the star Sirius. Sirius is the brightest star in the night sky, so you could guess it might be one of the closest. And in fact, it is. Only two other visible stars are closer. One is Barnard's star, which is very faint, and the other is Alpha Centauri. But you can't see Alpha Centauri from where Newton was in England because it's too far south in the sky. So for him, Sirius was a really good choice. And the idea that he got from Gregory was to assume that Sirius was as bright as the sun, and then calculate its distance based on that. But it's really hard to directly measure how bright the sun is compared to Sirius, since the sun is out only during the day and Sirius is out only at night. So you need to use something else, something that is out at night, as a surrogate for the sun, like a planet that's reflecting the sun's light. So you wait until one of the planets is as bright as Sirius, and you then use the amount of sunlight being reflected by the planet to figure out how bright Sirius appears compared to the sun, and from that you can calculate the distance to Sirius. Newton concluded that Sirius is 1 million astronomical units away, or 1 million times further away than the sun, which works out to 16 light years. In reality, Sirius is only about half that distance. It's 8.5 light years away. But Newton was off by less than a factor of 2, so he did have a realistic understanding of the distance to nearby stars like Sirius.
Newton is also famous for co-discovering calculus and proposing the theory of gravity. Both of those certainly had an impact on astronomy.
They did. Calculus, which Newton was working on about the same time as the German mathematician Gottfried Wilhelm Leibniz, is a powerful mathematical tool that gets used all the time in astronomy. And in 1687, Newton published his Principia Mathematica, which introduced the concept of gravity. Initially, as we've mentioned in previous episodes, Newton was accused of introducing gravity as a magical concept, meaning literally a concept from natural magic, since it violated the Aristotelian principle that objects need to be connected in some way to have an influence on each other, whereas gravity involves spooky action at a distance. But despite how spooky gravity was, Newton's equations worked so well that eventually people got used to the idea, and now there was an explanation for how the Earth moved around the sun and how all the other planets did too. That meant that you not only didn't need Aristotle's planetary spheres, you also didn't need Descartes' matter vortex filling up space. So the space between the stars and planets could be an empty vacuum.
Now that Newton had a sense of the distance to the stars, how big did he think the overall universe was?
The answer to this was something he derived from his theory of gravity, because one of his younger contemporaries, a British clergyman named Richard Bentley, asked him a question. Bentley wanted to know, given his theory of gravity, what would happen in a universe in which the matter, the stars, are initially distributed evenly and with perfect symmetry. At first, Newton didn't understand the question, and he didn't realize that Bentley was thinking of a universe where matter is literally perfectly balanced. So he said that wherever the matter was clumped together a little bit, gravity would then pull it together even more. But that would mean that the universe isn't gravitationally balanced, so it isn't stable. Over time, the stars would move as they got pulled towards each other by Newton's gravity into denser and denser clumps. Yet, people have been observing the stars for thousands of years and keeping records of the stars' positions, since the time of the ancient Babylonians, and nobody had seen them moving. They looked stable. The truth is that they do move, but they're so far away that their motions are imperceptible to the naked eye, and people in the ancient world didn't notice their motions. But this answer didn't occur to Newton, so he came up with a different explanation for why they seem stable. He reasoned correctly that if the universe were of finite size, or if the matter in it were unevenly distributed, then gravity would pull the stars together over time. But since the universe seems stable, he concluded that the universe must be infinite in size and have its matter perfectly evenly distributed. That way, each star is being pulled on equally by gravity from all directions, and so every star remains in place.
Isn't it kind of obvious from looking up in the night sky that even the nearby stars aren't evenly distributed? And Galileo had established that the Milky Way is a dense band of stars, so we don't look up and see a big perfect grid of stars that surrounds us and fills the whole universe as far as we can see.
We don't. It appears that it never clicked for Newton that the Milky Way is a huge problem for his theory, so he settled for arguing that the local stars are kind of symmetrical around the sun, and he then argued that God must occasionally nudge them to keep them in place so they don't collapse. That didn't satisfy everybody, but the idea that the universe is infinite in size stuck, because humans are bad at imagining how space could be finite in size. To keep space finite, you either have to imagine that space can be bent into a closed shape like a four-dimensional sphere, an idea that nobody had at this time, or you have to imagine an edge to space. But as soon as you imagine an edge, you start imagining what's beyond the edge, and so your picture of a finite universe becomes infinite again. As a result, many astronomers were willing to go with Newton on the idea that the universe is actually physically infinite in size. And that's even a respectable opinion among astronomers today, though they will admit that it's an assumption they can't prove.
Before we continue, I'd like to take a moment to thank our patrons who make this show possible, including John C., Alice C., Sean S., Luis M., and Jason G. Their generous donations at sqpn.com/give make it possible for us to continue Jimmy Akin's Mysterious World and all the shows at StarQuest. You can join them by visiting sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you in part through the generous support of our sponsors, including Aaron Ferguson Electric and Automation at aaronv.com, AARONV.com. Making connections for life for your automation and smart home needs in North and Central Florida. Jimmy Akin's Mysterious World is also brought to you in part by Catechism Class, a dynamic weekly podcast journey through the Catechism of the Catholic Church by Greg and Jennifer Willits. It's the best book club, coffee talk, and faith study group all rolled into one. Find it in any podcast directory. So, Jimmy, we've arrived at a point where people have a very different understanding of the universe than the ancients did. It's no longer a set of nested spheres, with the last one a little bit beyond Saturn. Now, the universe is a seemingly infinite sea of stars, with the sun being just one of those stars, and with the Earth and the other planets going around the sun. That sounds a lot more like the modern view of the universe, but it isn't quite the same. There's nothing in that about galaxies, for example. So how did we get to that concept?
Now that people knew that the Milky Way was made of stars, some scientists, or natural philosophers as they were called back then, started thinking about what shape it must be. Since it's a band of stars that wraps all the way around the sky in a big circle, that suggests we're inside of it, which we are. But that didn't tell us what its overall shape was. For example, it might just be a big distant ring of stars, kind of like Saturn's ring, with us as a little point in the middle. So people proposed different ideas for what its shape might be, and some of them were really weird and unworkable. The correct basic idea was hit on by the German philosopher Immanuel Kant. He lived in the 1700s, and if you're a fan of philosophy, you'll know that Immanuel Kant is the most influential philosopher in the modern period, which began in the 1400s. That's not to say he's the most correct philosopher in the period, but his thought was so comprehensive and revolutionary that he is the most influential. Basically, he's the most influential philosopher who lived after Thomas Aquinas. And so it was Kant who ended up being the one who hit on the basic idea of what the Milky Way shape is.
So how did he figure that out?
Kant knew that astronomers were seeing cloudy patches in the little cloudy patches of light in the sky. The Milky Way was the biggest, but there were smaller ones too. These cloudy patches are called nebulas, from the Latin word nebula, which means fog, mist, or cloud. Kant had a younger contemporary, the Swedish philosopher and mystic Emanuel Swedenborg. Swedenborg was a really weird psychic guy, and we will be talking about him in future episodes. Some years before Kant published his theory about the Milky Way, Swedenborg had proposed that these cloudy nebulas were whirlpools of matter that were slowly condensing to form stars and planets, kind of like in Descartes' vortex theory of the universe. So this is the origin of the nebular hypothesis of how solar systems like ours are formed. And it seemed confirmed by the fact that our solar system is like a flat disk, with the planets all orbiting in a single plane with the sun at the center. Now, Kant noticed that all of the different small nebula in the sky looked like ellipses, and that meant they couldn't be spherical, because a sphere looks like a sphere no matter what angle you view it from. But a flat disk will look like an ellipse from many angles. Kant thus realized maybe the Milky Way is like that. Maybe it's a big flat disk, and since we're inside it, we see it like a big nebular ring around us. So he hit on the right idea. The Milky Way is a big flat disk of stars. There were other details of how the Milky Way is structured that would be worked out over time, but it was Immanuel Kant who hit on the basic description of the whole thing. And when Kant's idea sank in, it matched astronomical observations, and so astronomers concluded that we are living in a big flat disk of stars.
So where did that leave the basic picture of the universe?
Because of the way the human imagination works, astronomers had the idea that we exist in infinite space. And within that space, we now understood the dynamics of our solar system as a system of planets moving more or less around the sun. And I have to say more or less because gravitationally that isn't quite true, but we'll need to leave that qualifier for a future episode. Beyond our solar system, we could see the closest stars with the naked eye, but beyond that, we needed telescopes. And the farthest stars we could see individually with telescopes, at least the early telescopes, were all in the Milky Way. So it looked like the Milky Way contained all the stars there were. The result was a very popular view, according to which the Milky Way was the only thing in the cosmos. In other words, the physical universe is an infinite expanse of space, and the only thing in it is the flat circular disk of stars in which we find ourselves. It's just the disk of the Milky Way in an infinite sea of darkness. As they say on the TV show Babylon 5, we're all alone in the night. And since the only thing in the universe was the Milky Way and everything else was empty, astronomers took to calling the Milky Way itself the universe. I mean, why not? It's the only interesting thing if the rest is just a big void. So you may as well call the Milky Way the universe. And that would remain the common view until the early 20th century.
So how do we discover that this isn't the true picture of the universe?
Well, not everybody was on board with the idea that the Milky Way is the only thing in the universe. It was a popular view, but there were still these distant cloudy patches in the sky. They might be smaller than the Milky Way, but that didn't tell us where they were. I mean, sure, they might be local nebulas that were collapsing into solar systems like Swedenborg and Kant and others proposed. But some astronomers noticed that some of these nebulas were different. Specifically, some of them were shaped like spirals, and as a result, they were called the spiral nebulas.
What would cause some nebulas to look spiral while others did not?
One possibility is that the spiral nebulas were spinning while the other blobby nebulas weren't. On the nebular hypothesis for how the solar system formed, you'd expect to start out with a big cloudy patch of gas that didn't have a structured shape, just a big blob. But as gravity got to work on it and started pulling it together, small differences in the velocity of gas and dust particles being drawn together in the center would cause it to start spinning around its gravitational center, and that would cause it to flatten out like a disk, and at some point it could acquire enough structure to look like a spiral. Thus, it could be that the spiral nebulas were simply planetary nebulas that were at a more advanced stage of their formation, while the blobby, cloudy nebulas were at an earlier stage of development. But the fact that some nebulas were spiral suggested they were spinning, and that was consistent with the idea that solar systems form out of spinning nebula.
Was everyone convinced by this explanation?
No, for one thing, we could see stars inside some of the nebulas. In fact, some nearby nebulas looked as if they were made of stars. These were what we would now call globular clusters, which, as the name suggests, means a big globe-shaped cluster of stars. So we knew that some nebulas were made of stars, and we'd already had the experience of finding out that the Milky Way, which looks like a nebular band stretching around the sky, is also made of stars. So some people proposed maybe the spiral nebulas are made of stars too. That would make them like faraway versions of the Milky Way. And since the Milky Way was often called the universe, just an island of stars in the great darkness, the hypothesis grew up that the spiral nebulas were actually island universes, just like the one we're living in. So at the beginning of the 20th century, so in the early 1900s, astronomers were very much split over the question of whether the spiral nebulas were located nearby here inside the Milky Way, or whether they were distant island universes outside the Milky Way.
How did they go about resolving that issue?
One of the ways they tried to do it was by holding a debate. The debate occurred on April 26, 1920, at the Smithsonian Museum of Natural History in Washington, D.C., and it's super famous as an event in the history of astronomy. It's called the Great Debate. Initially, 1920 was a pretty interesting year. As Marcia Bartusiak writes in her book, The Day We Found the Universe,
the year 1920 was one of achievements, illustrious, infamous, resourceful, and humorous. American women got the vote. Joan of Arc was canonized by Pope Benedict XV. Prohibition was initiated throughout the United States. An employee at the Johnson & Johnson Company invented the Band-Aid, and the U.S. Post Office ruled that children may not be sent by parcel post.
So that's what was happening at the time of the Great Debate. And yes, before 1920, people did sometimes send their children through the mail.
For all kinds of reasons. So, Jimmy, who were the participants in the Great Debate?
One was a young astronomer named Harlow Shapley. At the time, he was working at the Mount Wilson Observatory near Los Angeles, California, though he later became the director of the Harvard College Observatory in Massachusetts. Shapley took the view that the spiral nebulas were objects here within the Milky Way. His opponent was a more mature astronomer named Heber Curtis. He worked at the Lick Observatory, also in California, and he argued that the spiral nebulas are distant island universes.
So who won the Great Debate?
Actually, it was pretty inconclusive. Neither debater won a clear victory, which is actually the way a lot of debates are. Shapley essentially presented his theory that the Milky Way is really huge, a lot bigger than most astronomers thought. At the time, astronomers were still working out how to measure the distances of really far-off stars, and a common view was that the Milky Way was only 30,000 light years across. It was also thought that the Sun is near the center of the Milky Way. But Shapley had observations that he used to calculate a much bigger size. He calculated that the Milky Way is 10 times bigger than what people thought, that it is 300,000 light years across, and that the Sun is not near the center, but quite a ways towards the edge.
How do those calculations compare with modern astronomy?
They're not bad, but they're not great either. Shapley was right that the Milky Way is bigger than what was thought, but it's only 3 times bigger, not 10 times bigger. The Milky Way is 100,000 light years across, which is a third of the size that Shapley thought. He was right, though, that the Sun is not near the center of the Milky Way. We're actually about 20,000 light years from the center. So in science fiction writer Larry Niven's known space universe, where the center of the Milky Way has exploded, humans have about 20,000 years to evacuate known space before the wave of radiation gets here. In any event, in the Great Debate, Shapley largely just argued for his theory that the Milky Way is enormous. It seems he largely thought that, well, if the Milky Way is much bigger than astronomers thought, that would be an argument that the spiral nebulas must be inside this really huge Milky Way. So he didn't much argue what the spiral nebulas were, just that the Milky Way is a lot bigger than people were thinking.
And what about his opponent, Heber Curtis? What strategy did he use?
Well, he took the bait and argued that the Milky Way is 10 times smaller than what Shapley was proposing, in accordance with what most astronomers thought. But he did devote attention to the spiral nebulas, arguing that they were island universes. Marcia Bartusiak explains,
Curtis went on to focus on the spiral nebula, the subject that Shapley conveniently avoided. Curtis showcased his best evidence. He stressed that the spiral nebula displayed the spectra typical for collections of stars, not gas, that not one spiral had ever been found within the visible band of the Milky Way itself, that the spirals are primarily seen away from the ring of the Milky Way because obscuring matter blocks the view through the plane of our galaxy. He paid special attention to the many nova being sighted within some spirals. He showed that if the flare-ups in Andromeda were 500,000 light-years distant, their luminosity would roughly match those seen in our own galaxy. Any closer, and they would be far too bright.
But these arguments did not carry the day.
All in all, the two men were simply talking at cross purposes. Shapley primarily defended his new vision of the Milky Way, its unexpected bigness, while Curtis hammered away on his contention that the spiral nebula were far-off galaxies. In hindsight, each turned out to be partly right and partly wrong. Shapley argued for his larger Milky Way, true, but insisted that the spirals were local, wrong. Curtis still believed in a smaller home galaxy, wrong, but persevered in his belief that the spiral nebula were situated far outside the Milky Way and rivaling it in size, true. At the end of the day, it was a wash. Everyone, in essence, went home maintaining the beliefs they held at the start of the lecture. The data were so muddled that Curtis and Shapley could take the same facts and arrive at completely contradictory conclusions. At the time of the debate, there was no overwhelming evidence to settle the inconsistencies either way.
So despite its name, the Great Debate wasn't that great. It didn't settle the question, and nobody made a truly conclusive case.
It seemed like Curtis had a number of good arguments for why the spiral nebulas must be island universes. So why didn't they carry the day?
Because there was a really big counter-argument that was out there. One of Shapley's colleagues at Mount Wilson was a Dutch astronomer named Adriaan van Manen. Van Manen was very popular and well-liked, and he had a reputation as a really good observer. And one of the things he had been observing, even though he didn't have a metal nose, was the spiral nebulas. Specifically, he would look at a photographic plate of a spiral and plot the positions of various stars within it. Then he would compare that plate to other plates taken of the same nebula years later and identify the same stars and see if they had moved. And van Manen concluded they had moved over the course of just a few years. He first did this for a spiral nebula in the constellation of Ursa Major, or the Great Bear, known as M101. It was nicknamed the Pinwheel because it's a galaxy that looks like a pinwheel. And he concluded it was visibly rotating. Bartusiak explains,
if turning at his measured rate, M101 was completing one full rotation every 85,000 years. That meant if the pinwheel were truly the size of the Milky Way and located way off in distant space, the nebula's edge had to be traveling faster than the speed of light, an impossibility given Einstein's special theory of relativity, which said that no bit of matter can move fast enough to overtake a beam of light. Given what was at stake, van Manen followed all the precautions. He switched the plates of the holders to eliminate machine error, and he got a colleague to redo the measurements with a different machine to make sure there wasn't an instrumental error or personal bias.
Van Manen also measured other spiral nebulas and found that they were rotating too. Other astronomers started doing the same thing, and they also reported what Van Manen was seeing, visible rotation of the spiral nebulas over the course of just a few years. This meant that if the spirals really were distant island universes as big as the Milky Way, the stars at their edges would have to be moving near or even faster than the speed of light. But material objects can't normally move faster than the speed of light, and that would mean that the spiral nebulas had to be much smaller and closer, and that would put them inside the Milky Way. After these measurements, which were confirmed by multiple astronomers, only a few held on to the island universe theory, but some did, and they produced their own arguments for why the spirals must be distant universes. Bartusiak explains,
the duel over the island universes continued. Nothing would be settled until astronomers obtained a clear and unequivocal distance measurement to a spiral nebula, an observation so clear, so decisive, so comprehensive, that it immediately quelled all doubts.
The man who would make that observation was named Edwin Hubble. He was an American astronomer, and like Harlow Shapley, he was from Missouri. Hubble was also a very colorful character, and Bartusiak has lots of funny stories about him in her book. He and Shapley, despite the fact they were from Missouri, did not get along because they disagreed over the island universe question. But they still maintained a cordial professional relationship and corresponded with each other regularly. And in 1923 and 1924, Hubble started getting observations that would settle the question once and for all. He was studying a nebula known as M31, which is in the constellation of Andromeda. In Greek mythology, Andromeda was an Ethiopian princess who married the hero Perseus. And so the fuzzy patch in the constellation of Andromeda was known as the Andromeda Nebula. And as Hubble observed the nebula over time, he discovered a particular variable star in it.
What's a variable star?
It's a star that changes or varies its brightness over time. And there are several kinds of variable stars, and one of them is particularly relevant to our discussion. This type of variable star is known as a Cepheid variable. In Greek mythology, Cepheus was a king of Ethiopia, and there's a constellation named after him. In 1784, astronomers noted a variable star in the constellation Cepheus, and so variable stars of this type are known as Cepheid variables.
What's so significant about Cepheid variables?
Unlike other kinds of variable stars, there is a direct relationship between how fast a Cepheid changes its brightness and how bright it actually is. In 1912, the astronomer Henrietta Leavitt prepared a paper in which she documented this relationship. Leavitt was an interesting kind of astronomer. She was what was known as a computer, a term that was used for people, usually women, who were employed to do mathematical computation. So back in the day, a computer was a human being rather than a machine. Just like a typewriter used to be a person who writes with type instead of the machine they do it with. Now, as we'll hear in a future episode on the Manhattan Project, there also were lady computers working to help develop the nuclear bomb, although they didn't know that's what the calculations they were doing were for. Henrietta Leavitt did know what she was calculating. It was her job to look at photographic plates of stars and measure their apparent brightness on the plate. And she noticed that there was a relationship between how bright Cepheid variables were and how rapidly they changed in brightness. Cepheids can take from a day to a few months to go through their cycle of brightening and dimming and then brightening again. And Henrietta realized that the longer the cycle is, the brighter they get. That means that if you watch a Cepheid going through its cycle and measure how long the cycle is, you can use a mathematical formula to tell you what its absolute brightness is. Absolute brightness meaning how bright it would be if you were a certain distance from it. From that, it would be simple to take the Cepheid's maximum brightness and figure out how far away it is. In fact, by the 1920s, Harlow Shapley of Great Debate fame was considered the world's leading expert on Cepheid variables, and he worked out a mathematical formula describing the relationship between a Cepheid's brightness and the length of its cycle. And he himself was using the brightness of Cepheids to tell how far away they were, so he realized their significance. And that brings us back to the variable that Edwin Hubble found in the Andromeda Nebula. Marcia Bartusiak explains,
3 nights in February 1924 proved especially crucial. Over the 5th, 6th, and 7th of that month, he directly observed his first variable in Andromeda brightening by more than a magnitude, doubling its luminosity, a tremendous break. From the data he had on hand, he could now sketch a reliable light curve. The variable star went through its complete cycle from bright to dim and back to bright again in a matter of 31 days. From the length of this period and the shape of the curve, sharp rise and slow decline, Hubble now comprehended that he had captured that elusive and rare celestial beast, a Cepheid variable, a star 7,000 times brighter than our own sun. but it appeared so dim, the barest smudge on his photographic plate, that Hubble knew it had to reside at a great distance. It was, on average, more than 100,000 times dimmer than the faintest stars visible to the unaided eye.
And on February 19th, 1924, Hubble wrote Shapley a letter announcing his findings.
And here was the kicker. In the letter, Hubble used the exact same technique for gauging a distance to the spiral that Shapley had devised for mapping the arrangement of globular clusters around the Milky Way. Applying the Cepheid period luminosity formula that Shapley had derived, Hubble calculated a distance to Andromeda of around 1 million light-years. No more oblique evidence or convoluted reasoning such as Heber-Curtis was forced to use. The Cepheid provided a direct and indisputable yardstick out to the nebula. Andromeda was indeed an island universe.
In other words, Hubble politely threw Shapley's own Cepheid formula back in his face and showed that the Andromeda Nebula really was 1 million light years away, far outside even Shapley's own supersized Milky Way, which meant, in turn, that it was another island universe.
Shapley, upon reading the letter, immediately grasped that Hubble's findings spelled doom for his cherished vision of the cosmos. Harvard astronomer Cecilia Payne happened to be in Shapley's Harvard office when Hubble's message arrived. He held out the 2 pages to her and exclaimed, "Here is the letter that has destroyed my universe." Hubble was at last confirming the speculation that had been circulating through the astronomical community since the days of Thomas Wright, Immanuel Kant, and William Herschel. The Milky Way was not alone, but merely one starry isle in an assembly of galactic islands that stretches outward for millions of light years.
And that is how we found the universe. We now knew that the Milky Way is just one in a sea of island universes. Later in the 20th century, the term galaxy would come to replace the term island universe, and so we now refer to the Andromeda Nebula as the Andromeda Galaxy. We also have better measurements now, and we know how far the Andromeda Galaxy is away. It's actually like 2.5 million light years away, twice the distance that Hubble was able to calculate. It's also a lot bigger than the Milky Way, being about 220,000 light years across compared to the Milky Way's 100,000 light year diameter. And it's moving toward us. So in 4 or 5 billion years, it's going to slam into the Milky Way, and the two galaxies will end up merging, resulting in a joint galaxy called Milkdromeda. So you can look forward to that happening.
Nice. So what happened with Shapley after Hubble disproved his model of the universe?
He was okay with it. As we heard, he took Hubble's findings seriously as soon as he got the letter, and in later years, he went on to do important work on other galaxies. He was one of the first astronomers to realize that although galaxies are like distant islands of stars, they aren't unconnected islands. Just like here on Earth, we have archipelagos, chains or clusters of islands, like Japan or the Philippines or the Hawaiian Islands. In space, there are strings or clusters of galaxies that are gravitationally bound together. Shapley helped identify these clusters, including a particularly big nearby one, which today is known as the Shapley supercluster of galaxies in his honor. So despite the fact that he was originally wrong about the structure of the universe, he was a good scientist who changed his views when new evidence emerged and who went on to make important discoveries, which is a nice note to end on.
It is indeed. So, Jimmy, what further resources can we offer to the listeners and viewers?
We'll have a link to Michael Hoskin's book, The History of Astronomy, which is a very brief read, and it mostly covers stuff before the 20th century. We'll also have a link to Marcia Bartusiak's book, The Day We Found the Universe, which is primarily about astronomy in the 1900s and the 20th century, and hers is a particularly fun read. She really goes into the personalities of the different astronomers and their relationships and who got along and who didn't and who was an eccentric weirdo and stuff like that. So there's a lot of fun stuff in that. I highly recommend her book. We'll also have a video I mentioned about the speed of light not being infinite and what it would be like if the speed of light was infinite. We'll have information about Tycho's supernova, that Library of Congress article we quoted about Descartes' vortex version of the universe, and also a piece on whether the universe does indeed go on forever and how big it appears to be based on our current knowledge.
Excellent. So, Jimmy, what do we have for mysterious headlines?
Well, since we talked about astronomy today, I thought I would give us an astronomy theme for headlines. And the first article we'll have a link to is about how in 1994, various Los Angelinos started calling 9/11 to report this weird cloud in the sky. They went out, there was a blackout, and they went out at night and they saw this weird cloud in the sky they'd never seen before, and they thought it might be threatening in some way, like maybe it's poison gas or something. So they called 9/11. It turns out, because of the blackout, there wasn't the usual light pollution that if you live in a city keeps you from seeing the Milky Way. So actually they were just seeing the Milky Way for the first time, and it wasn't a threatening weird cloud at all. Now, also now that's from 1994, but more recent astronomical news, an article recently came out saying that not only has our solar system been visited by objects from outside the solar system, like Oumuamua, and which we could tell because of the way it swooped through the solar system that it came from outside the solar system. One of them may have crashed into Earth in 2014. And so we may actually have an extrasolar object that's already fallen to Earth that we have been able to know when it happened and maybe able to get some pieces of it and stuff like that. So check out that article as well.
Awesome. I remember as a kid the first time I went someplace that had sufficiently little nighttime light that I could see the Milky Way. And it is indeed an awesome thing to see. Take your kids to see it if you don't live somewhere like that. You blow their minds, and it's a great experience.
Yeah.
So that's it from us. We would love to hear your theories about the structure of the universe and how we discovered it. You can let us know by visiting sqpn.com or the Jimmy Akin's Mysterious World Facebook page. You can send us an email to mysterious@sqpn.com. Send a tweet to @MYS_world. You can join our StarQuest Discord community at sqpn.com/discord, or call our mysterious feedback line at 619-738-4515. That's 619-738-4515.
And I also want to thank Oasis Studio 7 for the video and animation work they do on this episode. They do a really great job. And if you haven't checked it out, be sure to go to youtube.com/Jimmy Akin and watch some of the videos versions of the podcast so that you can see all the great images and animations that Oasis Studio 7 has been producing. And while you're there, I am trying to grow my channel, so please like and subscribe and hit the bell notifications so that you always get a notification whenever I have a new video come out, whether it's Mysterious World or one of the other videos I do, like the various apologetic videos. So be sure to do that. Thank you.
So, Jimmy, what are we going to be talking about next time?
Well, this week we talked about how we found the universe. So next week we're going to be talking about things coming down from the universe. It came from outer space to Earth. Specifically, we're going to be talking about reported UFO crash debris and the scientific analyses that have been run on this debris, including the famous UFO parts that were sent to talk show host Art Bell and are now known as Art's Parts.
Excellent. Folks, be sure to follow Jimmy Akin's Mysterious World in Apple Podcasts, Google Podcasts, Spotify, Stitcher, TuneIn, your favorite podcast app, or at the YouTube channel Jimmy mentioned, where you, again, make sure to hit the bell to get notifications. Get your very own Mysterious World t-shirt, mug, and more in our new merchandise shop at sqpn.com/merch. You want to get one of these great new shirts. And you can find links to Jimmy's resources from our discussion and links to the mysterious headlines on our show notes at sqpn.com/mysterious. And remember, to help us continue to produce the podcast, please visit sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you by Fearvento Law PLLC, now assisting clients with expungements and set-asides of Michigan convictions. To learn more, call 231-202-3321 or go to fearventolaw.com, FIORVENTO law.com. Jimmy Akin's Mysterious World is also brought to you by DeliverContacts.com, offering contact lenses at low prices with free delivery. Visit DeliverContacts.com. Until next time, Jimmy Akin, thank you for exploring with us our mysterious world.
Thanks, Dom.
And once again, I'm Dom Bettinelli. Thank you for listening to Jimmy Akin's Mysterious World on StarQuest.